Log on, tune in, find out. Another good idea from Cambridge.
To welcome Eric Sommers from the University of Massachusetts at Amherst, and he will tell us about two partially ordered sets arising from nilpotent orbits.
Great, thanks Pramod, and thanks for the invitation to come out here for a couple months. I'm enjoying myself halfway through. The title couldn't be more accurate. I'm going to show you one partially ordered set and another partially ordered set and make some comments about the relation between the two. Both partially ordered sets are just souped up versions of the partially ordered set coming from nilpotent orbits, which I'm showing you over there. And the idea behind it, the first one, not sure I have a real good idea of why this one is so interesting, other than it's related to the second one, which is related to the duality on nilpotent orbits when you restrict to the special nilpotent orbits, which is a subset of this. See, this diagram is not symmetric. Doing this, and so that was work of Spaltenstein, and then I did some work, and then Pramod did some work extending that, and this is sort of maybe the next take on it, explaining some of that work. But anyhow, so let me define the two posets. So the first poset is going to be related to B-stable ideals or subspaces of the nil radical. And then the second poset will be related to pairs of nilpotent orbits. And here the idea is to work not just in the Lie algebra, but just from the outset to also team up with the dual Lie algebra, the Langlands dual Lie algebra. And that's how the second poset will be constructed. So just if any letter here doesn't seem familiar, please let me know. I'll be working over C, although some things can certainly be done in good characteristic. And the first thing I want to talk about, to motivate this part at least, are the Springer fibers. Recall that we have the flag variety, G mod B, and if we pick a nilpotent element from the set of nilpotent elements, then the Springer fiber are those flags which have some condition involving the nilpotent. So this is the adjoint action of the inverse of the element corresponding to the coset G mod B. On this variety, we have the action of the centralizer of the element, just clear. So for example, the subregular, not the biggest orbit in G2, but the second to biggest one under the partial order under inclusions of closures, you get four projective lines attached 3 points like this. We have four P1s. And so I want to describe how you could see this. Why are we interested in this? Well, we're interested in these varieties because the Weil group acts on the cohomology, the Springer representation. In fact, that you call the top action related to the Springer representation, but we want to know the total action here. And then we also want to know we have this action of this group, the centralizer acting. Of course, the connected part won't do anything, but you do have that action, and you're really interested in how the component group acts, which is what happens when you mod out by the centralizer, this little finite group. So you want to understand these actions. Well, I don't have anything interesting to say about this part. Well, in fact, what I'm talking about now is not, I don't have, just sort of recalling previous work. This is hard to compute if you want to know this Weil group action. As far as I know, you have to actually compute it for all elements simultaneously. You can't just say, I want to take this particular nilpotent element and figure out what this representation is. You have to, say, following work of Shoji, put all the put all the orbits together, and then you have to actually know the Springer correspondence to begin with, which again is what happens at the top. And then you can solve a system of equations and actually determine what these things are. But if you are only interested in the cohomology itself and the A action here, then there's actually a direct way where you can pick an element and try to understand it. And that's the work of this paper that it's really the motivation for this part of DiConcini, Lustig, and Procesi, where they just basically give the method for doing this. So if you want a specific Springer fiber and you want to understand it, then this is, I think, the way to go about understanding it. At least, I mean, of course, there are ways to do it in the classical groups. You have Spaltenstein's work in type A, and you have other work in the classical groups where you actually can get an affine paving of the Springer fibers. But I'm looking for something more systematic. You can embed E in an SL2 triple, where the H part is the semi-simple, and decompose it under the action of H, or add H. Let me just describe how you can decompose the Springer fiber. You have a parabolic, as usual, attached to the greater than 0 space. And here are some results from this paper, the DLP paper. Number one, if you intersect the Springer fiber, I mean, I guess if you go back to Spaltenstein's work, the idea is that you can just look at the Schubert cells, and they will intersect the Springer fiber. If you set it up properly, they'll intersect the Springer fiber and give you affine spaces. Well, I mean, I guess that won't happen in general. But you have this result that if you intersect with a p orbit, so you take each p orbit on G mod B, and you intersect with the fiber, then this is smooth. Okay, and we can call, let's give this a name, say YW, where W is an element of the Wahl group. So the p orbit, we can index p orbits by coset representatives. So let's just pick a representative there, W. This variety is smooth. 2, there's a C star action on this variety, and when you contract it, then you get a vector bundle over the base, which is also smooth. So, I mean, I'll just choose some. I guess this is a union of BXBs, and I'll choose some. Yeah, so take the shortest coset representative, let's say. So WP is the Wahl group. Or P, or something like that. I'm not going to focus too much on that, but there's a Wahl group element, and if you take the BWB for that, then this is what you get. So you have this vector bundle over the base. And we can define this base purely in terms of, I'll explain this I in a second, purely without regard to the larger situation. Okay, what is I? I, contained in G greater than or equal to 2, is a B-stable subspace. Is B-stable, let's just say is B-stable. Okay, so maybe just starting over, what you find is that if you start with the Springer fiber, you're naturally led to, as you look over all the orbits that intersect this, each one will produce for you an ideal, meaning a subspace of this G greater than or equal to 2 space, which is stable under the Borel. Okay. So the only ones that will arise in this picture are those that are contained in these spaces. You won't of course, you won't get all of them because you have this condition where the E which is actually giving you this space, must show up in the ideal itself. Okay, but anyhow, given a Springer fiber, you have a finite list, a short list of such I that show up. And then you can define this variety. It's defined just like this. It's just the same definition as a Springer fiber, except instead of the full nil radical, which is your largest subspace of the nil radical, you have these sort of smaller ones. And what I like about this picture is that even though you can go over different orbits, you might be dealing with the same base space. Okay, and then where does this I come from? Well, I'm not going to give you the definition, but this comes from W. So once you nail down this W, you could take the roots that are set negative by W, and then somehow that will produce for you this ideal. Okay, so this is smooth. So this is smooth variety, and so somehow you can understand the total Springer fiber in terms of these smaller erasers are over here. In terms of these smaller varieties. So in particular, I guess we still don't know in the exceptional groups if there's an affine paving. But one way you could prove it, you could just try to focus on these smaller ones. If you could prove the affine paving for these, then you would be done. In particular, if we don't know if the list of all i's that will show up, I mean, a priori, but you will always get I equal to the greater than equal to 2 space. And that will produce for you the little flag variety for the parabolic. So that's an example.
But are these just the conormals in the Schubert variety that come down to the cotangent bundle that come down to the Springer, which have, well, I would tend to say come down to the orbital varieties, but you're looking at the dual picture. So you should somehow start off with a conormal bundle in the cotangent space. Look at the moment now.
Okay, yeah, I mean, I guess, yeah, so this is maybe, this is what I don't know if this is what you're saying. You could look at this projection, and then the fiber over the,
yes.
Yeah, that's another way to look at this. If you take E in here and you look at the fiber over E, then that's this YI. Yeah, so that's another way. So look at that, and then you could do this for any ideal, not just, in fact, this is sort of what I want to talk about. You do for any B-stable ideal in N. By B-stable ideal, I just mean a subspace of N which is stable under the Borel. You could form this vector bundle and map it to the Lie algebra, and over the open orbit, you would take this fiber, and that's always going to be smooth. That's the same proof that's given in the DLP paper. Now there's one more piece of information that I wanted to mention, which is that the component group acts naturally on this. So AE acts on this sort of little baby Springer fiber, the smooth thing, and in fact this thing is not connected. This thing is not connected, perhaps, and you have different components, and they're all isomorphic to each other, and it just permutes those components around. So it acts on this, and it permutes around, permutes transitively the connected components. So that's how you can capture the A action as you reconstruct your variety from these YW. So in fact, there's a partition of the variety into these YW, from which you can recover the cohomology of the whole thing from the cohomology of these, which can then be recovered from these since you have a vector bundle here, and the A action is just permuting around the cohomology, the components here, so it gives you the action on cohomology. In fact, what I'm interested in this most general situation, is the stabilizer of a component. So you could define K sub I. This is going to be a subgroup of the component group. It's only defined up to conjugation, up to conjugacy. This is just defined to be the stabilizer of one of these components. So if there's only one component, then you're getting the full group.
I think maybe you should say that this action really is preserved in the leaf. So it is like the zero section of the boundary.
Okay.
So this, I think, could be
Okay. The zero section of
of this not vector boundary.
Right.
Fine boundary, because it's really not no linear structure.
okay, and you mean the C star action that's acting?
Yeah.
Yeah. So there's a C star action here, and it really pushes it
it's
down.
like
to-
a compact variety with respect to action. The limit of any orbit lies inside.
Okay. Anyhow, that was some advertisement for this result. What did I want to say? Well, there's more shown in the. I mean, there's lots more shown in the paper. Let me just mention that in this paper, in general, we have the result. We have a direct result that there's no odd cohomology. For the Springer fiber. I guess we could have already known this again by this way of Shoji, of putting everything together and computing all the cohomologies at once, but that would be for rational coefficients. Here we also get, there's no torsion, I think is the first way we get that. Okay. What else? And in the classical groups, this is where, in the non-type A, we actually have an affine paving constructed once we have this picture. Okay, so what I'm interested in is taking so this first post set that I want to talk about is taking all the ideals, not just the ones that are in this greater than or equal to 2 space, and forming this variety and then attaching this group to the ideal. Okay. So what I want to say is, I mean, this group is interesting also. I mean, if you're interested in the functions on the orbit or on an orbit cover, this group is controlling, if you took functions on this, it's not a cotangent bundle, but on this bundle, you would be getting functions not on the orbit, but you would be getting it on a cover that's being controlled by this group. So there's some natural, some nice reasons for considering this group. And here's the first post set. So the idea is to define two ideals. I1 is equivalent to I2 if one is included in the second and they have the same saturation when I act on them by G, and they have the same group. So once they have the same orbit, we could talk about, do they give you the same group? Again, this group is only defined up to conjugacy. So this idea is even implicit in the DLP paper. So the post set that I want to construct, so the set is the equivalence classes generated by this relation. Okay. And that turns out to be a reasonable thing to do. And what's the partial ordering? One ideal is less than another so one class of ideals is less than another, if you can find representatives, I mean the most obvious thing, if you can find representatives, one included in the next. So these are just representatives for each class. Okay, so that's the post set. Why do I think it's interesting? Well, one result which is really, I think, kind of hidden in the literature is the fact, so how did Mizono, I mean, so I guess I'm talking about very classical things, at least for the people present. How do we compute the partial order on nilpotent orbits? So the set of nilpotent orbits, of course, one is included in another, one is less than another.
Basically, somehow, in this picture, you didn't have all eyes, you had only the G greater or equal to 2.
Right. So now here I want to take all I want to take all ideal, I want to take all B stable subspaces.
But then what is Ki?
So in this, I was just motivating it from their paper.
But what is Ki? Because before Ki was
Oh yeah, I sort of skipped around a little bit. So it's the same, it's the exact same definition. Actually, this definition would work fine, but then Joseph was pointing out that you could do this in general. And so for any ideal, for any B-stable subspace, you can perform this construction, and you get this variety, and you have the action. I mean, I've been thinking a lot over recent years about these subspaces. I think they're interesting. I mean, combinatorially, they're interesting. The number of subspaces is the Catalan, is the generalized Catalan number. So you can try to make connections to clusters, and I mean, this is not as sexy as clusters, but you know, you could try to make connections in that direction. But I think also, I mean, as a way, I mean, you have orbital varieties, which are also these B-stable subvarieties of the nil radical, and somehow these are just a little bit easier to control because they're subspaces. But so maybe you can capture some of the information that you would really want to get by looking at orbital varieties. Anyhow, so if you take the set of these subspaces and you make this equivalence relation, right, so what's the motivation for this? Well, if you forget about this group here, then what I was trying to say was that the partial order on nilpotent orbits is just this. This is how you would compute it. So you have this result of Mizuno. This is what he did case by case, and then I just proved a general result, which says that the partial order on nilpotent orbits given by inclusion is just the same as inclusion of ideals of these B-stable ideals. I mean, every orbit arises, the G greater than or equal to 2 space will hit every orbit. And then you look at all ideals which hit a given orbit, and then you look at the inclusion amongst these ideals, and that's basically how Mizuno separated the orbits out in E7 and E8. Okay, so that was sort of the starting point, and then why not attach this group and get this partially ordered set? So I could just show you what you get. Plenty of time. So that's our first our 0th poset, the poset of nilpotent orbits. And now we attach this extra bit of information. So because of this result, we're extending, we're getting more than the set of nilpotent orbits. I don't know if you can see this, but I've attached the finite group K that you get over here. So it's not, and for them just doing F4 here, there aren't that many non-trivial component groups. There's an S2 down at the bottom, and you get both subgroups there. There's an S2 at the top, and you get both subgroups there. And then the most interesting thing is you get this S4. Now you can ask which subgroups of S4 show up, and you get, you might think you would get kind of like the Coxeter subgroups. That doesn't work. You're not going to get the trivial group because of this fact over here that the component group, I mean, it's related to what's going on in the Springer fiber, and we know in F4 you don't get the sign representation when you study the A action on that middle nilpotent orbit. So you can't expect to get the trivial group, because then that would mean, well, I didn't explain this very well. If you induce from this group, that character has to show up in the Springer representation. So that doesn't happen. So you're not going to get the trivial group, but then you might think, okay, maybe I just get all the other Coxeter subgroups. But then this weird thing happens that you get a dihedral group. Still don't really understand that in general. Same thing happens in E8 with the S5 orbit, that you pick up a dihedral, I guess you pick up the same dihedral group. You also miss the trivial group. But what's a little bit of a mystery, so there is at least some mystery here, which is I don't know what happens in the classical groups very well. I've asked around, well, I guess I've asked a couple of people, what are the, so we know if you go to the top cohomology in the Springer fiber, we know which characters appear for, we know which irreducible representations of the A group appear, because that's how we know how to compute the Springer correspondence. But what we don't know is if you take a component, what is the stabilizing subgroup? So let me write that down. Here's the answer for F4, but in the classical groups, okay, I'll write it over here.
If I understand correctly, these I's are determined by the affine Weil group.
Sorry, say that again?
If I understand these correctly, these I's are just determined by the affine Weil group.
Well, there is you're right, there's a whole sort of story of how there's a connection with the affine Weil group.
And
If you take like the Xi arrangement, then
I was thinking of Peterson's work.
it's also, yeah, I mean, so sort of like,
So-
there's a whole sort of thing that grew up after Peterson's
So
work, but he only dealt with the abelian ideals. I don't know if he,
no, it works in general. The whole construction works
well,
in
I
general.
mean, you have
It does
results
work,
of,
I can assure you.
no, I know, but I was going to assign it to Cellini and Pappy, who first sort of
Well,
unified.
it's the same thing.
All right.
I mean, you know,
I mean,
you don't have to ascribe it to anybody else. But the
okay,
point is that then, so you now have a map from the affine Weil group
yeah,
to, well, I would call it double cells in the Weil group. Right? There's a double, I mean, there's a Springer map that takes you from the Weil group to conjugacy Clark to nilpotent orbits, right? And I mean, Springer just gave a way of describing the nilpotent orbits associated. He just took the G saturation set of N intersection W of N,
okay.
right?
That wasn't
So
Carter?
What?
That wasn't Carter? Okay, it doesn't matter, doesn't
No,
matter.
it's the same thing.
Okay,
Well, it doesn't really matter.
Okay.
I mean, whatever.
all right, yeah.
So now you're going down from the affine Weil group.
All right,
And in principle, that's a bit richer. I mean, you
yeah,
have a
no, I
bigger
mean,
kernel.
I don't know how to bring that whole, so what I was ascribing to Cellini Pappy, but maybe well, Peterson never wrote anything down, so it's not even clear that we could even verify it, but there is a bijection, maybe this is interesting, between the ideals,
Everything he said was written down.
there's, and regions, the Xi arrangement, we should call them dominant regions of the Xi arrangement.
You mean B-stable ideals?
Yes, it's B-stable ideals in N. So in type A, here's the Xi arrangement, a part of it that lies in the dominant chamber, and you have 1, 2, 3, 4, 5 regions, and those each correspond to 5 B-stable ideals. You could take so here we are in type A2, you could take this, you could take this, this, I'm just taking root spaces in the obvious way, and the 0, and there's a bijection here.
So does this factor through the Springer map? I mean,
I don't know. I'm gonna have to think. I don't know anything. I don't know much more beyond this in terms of. I mean, there's she had already proved SHI. She had already proved that there's a nice minimal element here. That's just 1, and that's just 1. That should be an interesting element. I don't know. Maybe for the abelian ideals, people have proved lots of things about it, but I don't know in general. Anyhow, let me just state this open question. This open question, what Ki arise in the classical groups? Of course, type A, there's nothing going on. All the groups are trivial, but in the other classical groups, you get elementary abelian groups, you get product of S2s, and you're no longer you can't really be guided. I mean, there's tons of subgroups here, not just the Coxeter ones, but other ones. And already there's something interesting when you start to see S2 cross S2, because you can get all 5 subgroups can arise. You can get the trivial, all 3 order 2, and then the whole group. By the way, you'll always get the whole group, that's clear. But you can also get 3 subgroups. So you can get 3 or 5, maybe you can even get 4, I can't remember. Now, but I've asked Van Leeuwen and I asked Lustig, and I guess probably you could go to Van Leeuwen's work and just sort of nail down what goes on, but that's harder than it sounds. But anyhow, so that's an interesting open question in this regard. Okay, so that's the first poset.
But if I understand correctly, the poset is just the inclusion relations of nilpotent orbit closures. The poset.
No, I've souped that up a little bit. So that was my motivation. My motivation was if you start with say how do you find how do you find these relations in F4? Well, I mean, we have a more advanced way. You could actually use the Springer correspondence, but when you go back, Mizuno, I think is the first who did this, and what he basically did is he used this idea which is hidden of using ideals. I think he actually did call them ideals, but it's sort of somehow separate from this later work that arose. And he basically was able to separate orbits by choosing different ideals. So then, the only thing I'm saying here that's maybe mildly interesting is there's a general proof of this fact that the ideals will separate orbits. And then once you have that, you can throw in this K group, and now you have a larger set of equivalence classes, which should be interesting, and it's connected to my second poset. So now here are my orbits. Now each orbit gets attached one or more subgroups of the component group, and now you have a nice other poset.
But again, the poset that you're talking about is the poset of these equivalence classes of ideas.
Yes, yes.
But what's that statement that they're equivalent to the inclusion of? What does this
Yes.
say?
So if you forget about that little group that you attach,
Oh,
then the inclusion of ideals
Oh.
tells you inclusion of orbits, which
it's
was-
equivalent.
is equivalent to, which
No.
which might have already been clear. I don't know.
Oh, no, maybe not.
Okay, so now in the second part, so I sort of feel a little bit embarrassed. I've talked about the second part a lot, but maybe there's a few people who haven't seen it before, and I've only given myself a half an hour to talk about it, so not a bad. I don't think, even though this part was older, I don't think I actually ever talked about it, so hopefully that was at least something interesting there. So LG is the Langland's dual group, dual Lie algebra, and in there you have the dual Cartan. So this is sort of fast way to defining this. If I take a point in my regular Cartan, then I'm going to associate two orbits to it. I'm going to associate one, which is actually in the dual Lie algebra, and the first, which is actually in the proper Lie algebra that I start with. So I'm trying to do everything with reference to G. So I start with X and H, and we define this. This will be relatively elementary to define, and then this will use the associated variety. So it may be more complicated to define because you need to know the Springer correspondence to compute it. If you want to compute these two things, all you need to know is data which people have looked at, especially in this audience, have looked at for a long time. You need to know the integral roots and the singular roots. So the main data we need are the integral roots. So phi is the roots. The integral roots, which are those roots that take integral values on this point in the Cartan, and the singular ones sitting in there where you get 0. Then the integral roots give us a subdiagram of the extended Dynkin diagram and hence give us some Lie algebra, some subalgebra of G. So I just take all the root spaces in this subsystem of roots, and then the singular roots give us, more specifically, a Levy subalgebra in this Lie algebra. So these give us a Levy subalgebra here. And we'll call that Gx0. So the big one gives you something in the extended Dynkin diagram, but when you perform this operation, you can only get something in the actual Dynkin diagram of the previous one. So for example, in C3, here's what turns out to be an interesting point to choose. Alpha 1, alpha 2, alpha 3. Theta is the highest root. So negative theta attaches and gives me my extended diagram. And I'm interested in getting something which is not actually a Levy of the original diagram. Let me just start out by putting 2 here and 1 here as my values. What are these values? These are the values, so I have this x. These are just, I'm just doing like a weighted Dynkin diagram. So for example, this is the value that alpha 3 takes on x. And let me leave a and b open. So for example, so that puts a condition, because these are not independent, this puts a condition that 2a plus 2b equals negative 3, or a plus b equals negative 3 halves. So the 2 interesting examples would be, just to show different things that can happen, if you make them both equal, then you really will isolate out the 2 extreme roots. So the integral one will be c1 plus c1, and the 0, there won't be anything there. There's nothing integral. Whereas, let's put this back over here. Whereas if you choose 2, a equals minus 1, b equals minus a half.
That C1 cross C1 is somehow got by deleting alpha 1 from the alpha 1 and alpha 3, is it?
Alpha 1 and alpha 2. Alpha 1 and alpha 2. So I'm looking at the integral. I'm looking at my integral roots, and so clearly negative theta will be integral, and clearly alpha 3 will be integral. But I want to choose a and b so that nothing else up to plus or minus is integral. So it's like I've got a weighted Dynkin diagram, and I'm asking, what are the roots that are integral? If I doubled everything, I'd be talking even versus odd for most of these things. In this case, the integral, if you work it out, you pick up an extra by, well, I let a be negative 1, so alpha 1 will now be integral. So I'll get c2 plus c1. Right, so here I have negative theta alpha 1, and here I have alpha 3. Now I pick up a singular root. Sorry, I guess this is maybe not necessary to go through, but you do pick up the long root in this Levy minus theta plus 2 alpha 1 will now be singular. Okay, so you can get different things in this way. So now to define, we have 2 orbits to construct. Let's first define the easier one, O sub x. Well, we have, up top we have a subalgebra, and within it we have a Levy subalgebra. So what we're going to do is we're going to take the Richardson orbit, for the smaller subalgebra in the bigger one. Does that make sense? So if I have a Levy subalgebra, I can take the corresponding I can take the nil radical. So if I call this L and this L prime, I can take the nil radical for a parabolic for L in L prime, and that defines for me something. I can take the dense in that, and that's my Richardson orbit. And I can just take the G saturation of that. So that's how you construct OX. So in a way, I mean, it is related to this ideal picture from the part one in that the nil radical plays the role of an ideal in this L prime. Okay, so for example, if you were in case one from the example, you had C1 plus C2. You have no singular roots. So you have no singular roots, then you're talking about the Borel. So you're talking about the nil radical in C1 plus C2. And you can work that out, that gives you the partition 2, 2, 1, 1 in C3 for the orbit that you get. On the other hand, with 2 here, now you have a non-trivial parabolic in this C2. So you're going to get the subregular in that. And so just work that out, you get 2, 2, 2. C3. Those are 2 different orbits that you can get depending on the weight x that you choose. Okay, now the more complicated one is basically take the associated variety for the corresponding weight. In other words, think of x as a weight for the dual carton. Take the simple module for that weight of highest weight, but now I'll do this convention where you shift down by row. Fortunately, I have the dual row. And this is the simple representation or simple module for the enveloping algebra for the dual group. Okay, so we have that simple module, and then we know how to form the associated variety. Namely, you take the annihilator in this U of this simple module. That's an ideal. It's a primitive ideal by definition. And then you take the graded version of this ideal. So you have a filtration on U, and you take the associated, works that descends to J, and you take the associated graded for that, and you're talking about an ideal in what? LG, but we'll identify that with LG star. And that will cut out some zero set definition. We want to take the associated variety. So in other words, this is the open orbit in the zero set. For this ideal. So that's known by Borho-Berlinski, I think that's the right attribution, to be the closure of a single nilpotent orbit. And so we'll take the open orbit in that, and that's this orbit. So it has an easy definition, or an easier, maybe not so complicated definition, but if you actually want to compute it, then you have to know the Springer correspondence, and you have to play around with these two root subsystems. So there's an algorithm for computing it, at least when x is, so I want to focus on the case where x is actually dominant. And then we know there's an algorithm for computing this associated variety using the Springer correspondence plus you have to use truncated. You have to really kind of use the whole toolbox for this stuff. You can compute it. Okay. So in the last few minutes, let me state some results about this pair of orbits that you get. Well, so you could work over the entire dominant chamber, pick any x that you want, and look at all the pairs of orbits you get, OX and LOX. Maybe that's interesting, but it turns out, I was basically trying to recover work of a char, and what I noticed was that, and there's actually some other connections which I don't have time to talk about, but I noticed is that if you throw out certain x, then you do recover this work on the nose. So let me tell you the game. Maybe this has already been done. I'm not sure. The game is fix a W invariant form on our carton for each pair that we see that arises from this construction. We want to look at the following thing. We want to take the infimum of all the lengths of all the elements that we need, the dominant here, that obtain this particular pair. Okay, so if you see a pair, first of all, tell me all the x that give you that pair. You can work, you don't actually work that out, but it's just in terms of these subsystems that you see. But now the interesting thing is try to find the element of smallest length or smallest norm which can give you that pair. And what you find, so take the infimum, is you find that the minimum is not always achieved. So if the infimum is realized as a minimum, I guess we could call the pair O, LO. Well, every adjective has been taken. Nice, special, we'll just say it's achieved. The pair is achieved, and then that's the definition. Take those that are achieved in this way. So our second poset delta sub G is a set of all achievable pairs that's the set, and here the partial order is what? Is inclusion of the first orbit and reverse inclusion on the second. By which I mean if you have two pairs, and they're comparable if and only if the first coordinate of each pair are related in the usual order for nilpotent orbits, and the second coordinate of each pair is flipped around in the usual orbit for nilpotent orbits. So I'm just basically mimicking this work of Pramod. This is one of the main observations from that work, but now recast in this language. And so then the theorem extending that work, Spaltenstein's work, is that the flip map, namely now you have a nice thing to consider, which is you can consider the orbits that you get for G and the pairs of orbits that you get for LG. And you can define a map from one to the other by just flipping the order. So OLO goes to LOO, and then the interesting thing is that this doesn't have to be well defined, because this pair might not actually be a pair here, but it is when you're in this achievable part. So this is actually well defined bijection, and it's clear that it's order reversing. Okay, so you get this partially ordered set, and you actually have this map between two of them that reverses the order. And well, I had some other parts, but
On this achievable one or in general?
just on the achievable ones. So this really has to be, really have to do this, otherwise you won't, this part won't be true. So in a sense that's, yeah. So maybe I'll stop by saying that, but let me just say a couple of things in conclusion. Well, maybe let me show you the poset. It's very similar to this first poset, and make some statements about it. So here's the first poset with the groups, and now the second poset is with pairs of orbits, and now F4 is self-dual. So you have an orbit and another orbit, and one is big and one is small, starting with the regular and the zero, which is dual to the zero and the regular. And you get some interesting things in the middle there. You have these sort of non-special orbits which are dual to themselves, B2, B2, and the special one on the far left there, F4A3, is self-dual. So, and then the theorem trying to mimic this work of a chart is that this is a dual graph here. In this case, because we're in the same group. Now, I observe, but I don't totally understand. I mean, there's a way, basically, I'm lying a little bit, to embed this picture. You can embed this picture in the previous picture. Oops. Take this picture, and you can embed it in here. So this has some extra things that if you throw out, it's hard to see. Also, because I'm lying, because there's nothing on the far, you're missing that little triangle. Here, there's that little one right in the middle on the far left. You're missing that. And that's because in the Springer correspondence, you're missing the sign character. So up to this fact that you can be missing certain characters, I mean, maybe there's a generalized Springer correspondence going on, but the second poset is contained in the first. And that should be true in general. So conjecture, second poset, well, at least it maps to the first poset in an order-preserving way, and up to sort of the Springer problem of missing local systems, hence missing subgroups, it actually injects. So that's sort of my justification why the first poset maybe is more interesting than just in and of itself. Let me mention some other things that are interesting from this work, which is when you go to minimize, find these achievable pairs.
You get all nilpotent orbits in this one?
Say again?
You're going to get all nilpotent.
You always get all nilpotent orbits. You always get all nilpotent orbits occurring in a first coordinate or a second coordinate. But the mixture of the two, it's not, there's a tight connection, what you get. Yeah, you get, so let's see, you could always take,
But you mean you might not get all, ideals which given a given variety, because it might come into the second one.
say that one more time?
So you're looking at one of the orbits is the orbit closure of an ideal.
That's right.
So you're not getting all of them because it may occur in the other one. But you're not able to show by this method that every orbit comes from the associated variety of an ideal.
This calculation does, but my impression was that was already known. I mean,
It's known, but.
So this would be an explicit way. This would be an explicit way to see that.
So you didn't get everything in the first factor.
You get everything in the first factor, and you can get everything in the second factor. You just can't necessarily get them.
You get all pairs.
Yeah. So let me show you. I mean, actually, this is one of the reasons. I mean,
But why do you know you get everything then? I mean, is it just computing these
Yeah, just
polynomials?
computing it. Yeah.
Just knowing what the Springer
I guess I don't know any more than anybody else why you actually can achieve every orbit.
But sort of Rogan was doing it case by case.
Yeah, so it's the same thing. I mean, maybe it's a little, I mean, one thing I don't, well, first of all, that's not written down, and second of all, this actually shows you, I mean, I sort of skipped the whole kind of middle section, which I think would have been even more painful than some of this other stuff, but you associate, well, I won't even say, but it's actually in the slide here, there's a middle piece of data that you associate, which helps control and maybe makes it easier to make these calculations. And that's what I'm showing on this last slide. So these are actually the minimal points that achieve the pairs. But I've written it in terms of another piece of data, which is an orbit with a conjugacy class in the component group. That's the thing which plays a kind of intermediate role that wasn't really present here. And I've written it down like a weighted Dinkin diagram. So if you want to achieve the zero orbit, that's actually for L, I guess it's for L, O, then you would take just the zero character. And so on. And I've done it like a weighted Dinkin diagram. And there's two interesting things to point out, which is you'll always have 1/2 the Dinkin element, I don't know what other people call it, 1/2 H from our SL2 triple is always on the list. Is always on the list over there. 2, 2, 2, 2, we've taken half of it, you've got 1, 1, 1, 1. But you always get a weighted Dinkin diagram. So it's an extension, it's kind of a larger set of diagrams or of weights that should be interesting. They include all the Dinkin elements up to a factor of 1/2. The other thing is interesting is you see there's one, I wrote down 2A1, which is missing there. That's something that's not achievable in F4. I didn't get to do the example in C3, but this 1 and 2 example in C3 is an example of something not achievable in C3. That same idea in D4 gives you something non-achievable. There's a pair there for which when you go to minimize, you pop out and you don't attain the minimum. So that's why that blank is there. So that's interesting. And then the other thing that I've conjectured, but I don't know how to prove, is that all these weights should give you completely prime primitive ideals. And I mean, I don't have much evidence for it, but in rank 2 it works. And so take calculations of Joseph in B2 and G2, and you see that not only do you get, so he shows that all the 1/2 H's give you completely prime. And in B2, there's one more, and it would be on this list. In G2, there are 2 more that appear on this list, and those are completely prime. So it seems, I mean, maybe that's not quite enough information to conjecture that, for example, all these weights should be Goldie rank 1 for F4. So that, I think, is a good place to
So
stop.
some of these X's are going to be on the walls, I suppose.
Yeah, I mean, they'll be singular. So I don't know, so maybe,
Can you somehow prove that they're as low down as possible?
I mean, I think somehow this minimization is trying to set that up. I don't know enough on how these calculations.
And this is always the weight plus row or minus row, shifted by row.
Shifted by row. Yeah.
It would be, it would be nice to show that you can't get a, so you'd like to show that you can't get a smaller Goldie rank in the same chamber, in the same facet.
Okay.
So, so one of the things that is in my paper with Borrow is some positivity property of Goldie rings, even when you go to the walls, which is sort of more delicate. And so if you could show, which might not be too terribly difficult, that within the coherent family of Goldie rank polynomials, there's nothing of smaller Goldie rank. That would already be
Okay.
an extra. So Goldie rank 1 is very delicate, you know. Because but at least if you could show it was a minimal Goldie rank in its,
Yeah, that'd be nice.
it would be nice.
Yeah.
That might be easier.
So maybe you could explain that to me a little bit later. That'd be great. Well, thanks.
Are there any other questions or comments? If not, we'll meet for usual at 5:30 for drinks in front of the reception, and let's thank Eric again.